Now, so we term this, we say doing research with ML. And that's the part 2 of try to introduce each and every one of us to how can we benefit ourselves by kind of carrying out our research by incorporating machine learning method, techniques, algorithms, and their dimension. And we did describe last 2 weeks ago, that how machine learning is becoming a commonplace in almost all fields of human endeavor, that everybody as a researcher that want to be in line with be in tune with the latest in the field, that we just have to try to see, okay, how can we possibly incorporate machine learning to some of our research efforts? So in this respect, we started last week. We discussed extensively the introduction. We refer to the video that was recorded for that lecture 2 weeks ago. Sorry, we couldn't meet last week. So now, we refer to the lectures. We also discussed literature survey, and we said that these two, we assist them each other, because you cannot really write a clear introduction about what you want to do without knowing what has been done in literature. And we did describe briefly for us how we need to make sure we describe what we call what. You have to answer the question what, why, and how. So which is going to be a kind of problem formulation section. So we call it formulation of problem phase, formulation phase. So we have to ask the question, what do you want to do? So describe what you want to do in a very clear and simple sentences. Why are you doing it? And I said, why you have to approach it from 2 points of view. Why it is important, the importance of that particular topic to you or the solution you want to provide. And then why from the point of view of gap. Sometimes something is very important, but then there's no need for you to do it because someone already did the same thing and they solved it in a better way. So why are you trying to do it again? Just to reinvent the wheel for the sake of doing research? No. So we have to have gap, and that is where literature survey comes in. So we check the literature, see what has been done, and then try to see what is left for you to fill as a gap. So this is going to be part of why you have to do it. It's not enough to do. It's good to tell us the importance. If we don't solve this problem, what can we face? What could be the negative challenges? But then it's not enough. Rather, the gap is very, very important. So, and I want you to tell us, this is one of the things we are going to talk about today. Sometimes the fact that some researcher already published a particular topic that you are thinking of, it doesn't mean you have to run away from that topic. So I want us to take note of this. No, there are several ways you can come up with, you can identify gaps in the paper that has been published on the same topic you are trying to work on, even on the same data set. There are a lot of ways that you can come and contribute to your own quota there. So this is very, very important, because I've seen people, a couple of maybe people trying to say, oh, this topic is very nice. However, I saw that someone already published there. That is not just enough to leave the idea. Rather, you need to dig into that. What have they done? Try to do your literature survey clearly. So, okay, you wanted to work on maybe predicting a particular component, you want to predict the strength of material. Okay, see what they have done in that strength of material prediction, what have been done, several papers have been published. Try to look at it systematically. You will see that you have a couple of gaps, especially from machine learning point of view. See, from machine learning point of view, one of the two you need to look out to, the most important thing is accuracy. You see, the accuracy is the most important you have to check. How far have they gone in accurately predicting the component they promise to predict, like strength of material. Somebody is predicting the strength of material. What is the maximum accuracy? Check it out. Maybe they have been able to achieve only 92. Our target is always to go 100%. You have to check that one out. So this one way to check. So, okay, they have worked in that area. What is the gap? Oh, the accuracy is still very low. Sometimes you see them still in the area of 82 or whatever. If it's still less than 100, there's still something you can do. Even sometimes when you see that they've achieved 100, there's still other places to look into to check gap identification. Later, we're going to have possibly a video where I'm going to talk about gap identification in machine learning research. How do you identify gaps to be able to know how to come in and solve problems using machine learning? So if the accuracy is already 100% or close to 100%, then another thing you have to look into is how have they been able to do the problem, to solve the problem? What of robustness, what of consistency of the problem? That the problem solver can ensure they always achieve the same result? Or most importantly, try to check how many features. See, how many features did they use in solving the problem? That is the input. The input variable, the one that people call input variable, or as they call it, independent variables, as the case may be. How many independent variables were used? You want to predict strength of material, but you use maybe like 15 variables were used. Okay, this could be a place for you to come in as a gap that, okay, can I try to investigate this problem? Can I solve the same problem using less than 15 variables in what we call feature selection? So your own contribution, you want to contribute from the point of view of feature selection. Because feature selection will assist you a lot of things. Gathering 15 input variable before you can predict a single component is time consuming. It's costly to generate that kind of number, a huge number of features. If you can bring it down to maybe 3 features and you still achieve the same 100% or near 100%, somebody achieve 100%, now you reduce it from 15 variables to 3 variables and you're able to achieve like 98. That is excellent. When you look at the cost of gathering 15 variables, especially when we come to, let's come to medical application, for example. We want to diagnose and then we have to ask somebody to go and do medical tests up to 15 samples will have to be taken before you can use your machine learning diagnostic tools. That is too much. Especially in an environment where people don't have access to free medical services or affordable medical services are not there. Even when you have free medical services, it's still going to be a big burden if 1 million people have to do 15 tests for just a particular simple diagnosis. You can see the amount of financial burden that's going to be on the government or the responsible organization. So in this sense, if you're able to reduce it from 15 variables to like 3 or 4, or just in what we call feature selection, I think that's going to be a way that you can contribute. See, this is another way to look at it. So sometimes also you might want to also look at the data set, look at what they have done. Okay, what kind of method have they been able to deploy? Even sometimes the accuracy is there, but then what are the mistakes they are making? We talk about this, we call something false positive, false negative, and false positive. See, false negative and false positive. In medical application, if somebody is predicting and achieving maybe 97% accuracy, but all the mistakes being made are all false, they are making mistake of false negative. That is declaring people not to have disease, meanwhile they have disease. So diagnosing them falsely. And so what I was saying is that another way you can look into try to establish gaps in what have been done is, okay, in addition to try to see, okay, how many features did they use? Can I reduce this number of features? This is one way you can come in and try to improve the work. And then I say another way is even maybe we have a particular earlier work where they achieved 97% accuracy in predicting, in diagnosing maybe diabetes patient. And then we notice that the 3% mistakes are all coming from false negative. False negative means people that are actually having diabetes, the system is predicting that they don't have diabetes. So which is a very serious mistake in medical prediction. We don't want false negative because you end up letting people go home, relax, thinking they are okay, only for them to develop complications as a result of the mistaken diagnosis. So someone decided to, since the mistakes are on the wrong side, you can still decide to work on the same problem. Even though 97% accuracy has been achieved, or even 98, try to say, okay, can I solve it using other algorithms, using other method, deploying some other sensitive way of handling this problem, and you are able to maybe perhaps achieve the same 97% accuracy, let's say, the same 97, but this time around, you are able to reverse the mistake. All the 3% are now coming from false positive. False positive. False positive is also a mistake. We don't want it, but however, it is still a better mistake. You see, it's an acceptable mistake in medicine because you are actually saying that someone who is not sick, you are predicting that that person is sick. So he will go for further check in the clinic, and then the clinic will not say, oh, you are okay, everything is fine. I think it was a mistaken diagnosis. So this is a lesser evil when it comes to mistake that comes with predictive solutions. So this is another way that you can actually come in and try to add more. So there are several other ways. Like I said, there's going to be hopefully a whole dedicated video later to discuss how to identify gaps for machine learning intervention when you carry out research. Now, so we discussed that. We say, okay, you have to, we were actually revising the concept of describing why you want to do the research. And I said it has to be from 2 points of view. One, tell us the importance of that area, that problem you want to solve. And also now talk about the gap. So that was what took us to this explanation. So once you identify the gap, then you move on to how. How do you want to solve the problem? This is where you're going to mention, okay, we want to solve the problem using machine learning, if you especially specifically support vector machine. And also, after telling us how you want to solve it, tell us the why of how. What I used to call the why of how. Why this option? Tell us the reason why you want to use the method you want to use. Sometimes also literature survey will support you to do this, because you could have checked in the literature that SVM has been used in a lot of very sensitive application with excellent results. So you try to justify why you're coming up with this kind of solution and why machine learning is your option. Then we discussed about the methodology last time also, that the methodology what you're going to use is machine learning already has standards kind of set out procedure that you need to use when you are developing machine learning application or doing machine learning research. So, and then I remember we showed us this last time. So these are standardized. Of course, there's always room for a little bit of modification here and there. Okay, you start with your gather the data, pre-process the data, model building, model testing, do the tuning of the parameter. This is what we call the data preparation stage, which can have several things. Under data pre-processing, you might want to deal with outlier detection, missing value treatment. You try to treat the missing values. This outlier is very, very important, because sometimes it might not be obvious to you that there's outlier. There are methods that could be used to treat outlier. So we discussed them earlier. Some of our old videos, we can check them out. So, and also of other pre-processing you might do. Normalization also is what we can do here. You want to do normalization to try to reduce the effect of units on each of the variables of your data in your data set. So after you've done that, then you move to the learning from data stage. This is learning from data. So where you learn from data, you try to bring in your data, model development, validation, prediction finally. And once it is done with the necessary tuning, you build the model, you test the model. There's need to refine the model. Do I need to refine the model? Yes or no? Then I refine it. So it forms a loop. You keep going around until the model is okay for your liking or what you target to achieve. After that, you build the final model and then validate your model, prediction using the final model. So it's always good when you develop machine learning framework, when you have a machine learning research, it's always good to come up with the framework that you have used in developing it. Sometimes in this space, you might want to come in with ensemble method. We have discussed this extensively. So you have to let it appear in your framework. See, this is going to be the experimental description. So anybody reading your paper should be able to understand what you have done and be able to repeat what you have done. This is very important. And it's one of the issues that recently people have been talking about. That a lot of experiments are not repeatable. You cannot reproduce it. Reproducibility is one of the very important attributes that a good research paper should have. In fact, a standard journal, no standard journal will accept your paper if it cannot be reproduced. Because the moment the reviewers are checking it and found out that, oh, wow, there's no way we can reproduce this paper, there are a lot of information that are missing. Then that is a very big issue. We go into those ones later on. So when we come back to practical way of writing machine learning research reports, inshallah. Now, so having done that, that is under methodology. So you describe the methodology you want to use. What are the step-by-step you want to use in carry out this experiment? Are you going to use standalone machine learning algorithm, like k-nearest neighbor, support vector machine, or you want to mix them together, or you want to use hybrid? So this is the methodology where you're going to spell it out. After that, you move into the data analysis. Try now bringing your data to the system that you have designed. So what the here is, you are only telling us the procedure you are going to take. Then you spell it down in a very nicely sketched out flowchart diagram, flow diagram, and so many other ways, block diagram that you can use to describe the methodology. Let us know the flow of your experiment, how you move from one stage to another. So pictorial representation, as we know, is always sometimes very much interesting and easier to follow than writing so much text to describe the methodology. Of course, they're not mutually exclusive. In as much as once you have your diagram, it's always good you're going to have a summarized section where you describe each of the steps you have put into the methodology flowchart. So this is very important so that everybody will be able to understand what you promised to do or how you have done your experiment. After that, you move to the data analysis, purely doing your prediction. So doing the modeling, checking different parameters, checking different types. So the design, you have already promised in your methodology. Are you dividing into 80% training, 20% testing, and host of other method of partitioning the data? Once you are done with that, so you move to the discussion of results. So the discussion of results is very, very much important. And of course, the conclusion. So we call all this the analytical phase. So your power of analysis is very important. It will go a long way in actually convincing the reviewers to actually accept your paper or otherwise. See, because sometimes it's not just for you to reproduce, especially we used to see people when they talk of discussion of result, they only reproduce what is in the table and put it in the discussion. You have to go higher than just that. People can easily see what is in the table. You have, after the data analysis is done, you do the prediction, clustering, whatever type of machine learning analysis you have done. So the result usually represented in a table, in figure, but then in the discussion section, you need to do more than just reproducing what is in the table. You can see from the table that ANN is better than SVM. Yes, you can see directly from the table, but can you tell us something more than just reproducing what is already stated in the table? So you have to go to higher level of analysis. Okay, tell us what is the percentage improvement that support vector machine offer to the neural network. So talk in terms of this. So this is very much important. Also look at the implication of the results that you have achieved. So maybe after the data analysis, like I've mentioned here, yeah, like mentioned before, during the data analysis, the results will be there. So you have your table that will have the results. So this is SVM, this is k-nearest neighbor, this is decision tree, whatever method. Okay, what is the accuracy? This is 97, this is 96, this is 92. Explain to us what is the percentage accuracy. Maybe someone worked on the same problem before. It is always very good to make sure that you have a place for that person. So you need to compare your work with the person who worked on the same problem before. So, and then try to see, okay, what are you putting on the table that is better than what they have done? What is the improvement that you have actually achieved over the earlier published work on the same problem area? So another thing you have to make sure you try to mention in your discussion of result is try to tell us the implication of the error. You can see here that the mistakes are very glaring. So that's why you have to go, if this classification problem, you have to go into try to come up with the confusion matrix. Confusion matrix. What are the mistakes that are being made? See? So we have the true positive, we have the true negative, we have the false negative, and then we have the false positive. So we have those ones that are predicted to be positive when they're not supposed to be positive. Those predicted as negative, they're not supposed to be negative, here and there. So you have to analyze it. These are the problem we don't want. These are mistakes we don't want. However, as I mentioned earlier, this, if it is medical application, then false positive is a mistake that is welcome. I hope you will get me right. There's no mistake that is welcome, but some mistakes, you know, sometimes when you have two challenges, you pick the one that is lesser. If you don't have the option of solving the two problems at a time. So false positive is predicting that somebody is sick, meanwhile the person is not sick. We don't want it, but sometimes when we get it, we prefer it over false negative. False negative is telling somebody that you are okay, meanwhile the person is sick. So we don't want this kind of mistake. It's a serious mistake. This is a mistake that is manageable. See, in that case, I try to analyze my result from that point of view. Okay, let's go into the, under your discussion, you go into those implications. Now we can see that from our own outcome, we notice that the mistakes are coming from the false positive. Unlike the earlier work, though they achieved closer to our accuracy, maybe they achieved 97, now we're able to get 98. However, their own mistakes are coming from false negative more compared to our own, that way the mistake is on the high side of false positive. So these are kind of discussion. You try to bring out what are the implications of what you have done. How do you want us to really understand and appreciate the outcome of your experiment and the analysis that has been conducted. Now, this is if you are dealing with a classification problem. You'll be surprised that the same analysis we have done here, if we are actually developing an application for a production company that produces some products and send it to their customers, the opposite is going to be the case. In this case, false positive is not acceptable. False negative is welcome as a mistake. See, for example, any production company that they produce a particular product and they send it out to their customer, when they use machine learning to check the product for quality control, if the machine learning says it is good, meanwhile it is not good, that is called false positive. This is a mistake. We can manage it in medicine. We cannot manage it in industry. Because the implication is that the system is going to say that the product is good, and then you will ship a product that is bad to your customer, and the customer can take you to court or to the Customer Protection Agency, and then they can go on Twitter and all other social media, try to badmouth your company. So in that case, you can see that what was manageable here as a mistake is unacceptable here. However, false negative is saying that the product is not good. Meanwhile, the product is good. It was a mistaken prediction. We can still manage this. How? Because the country control men, we go there and check the product physically to see the mistake. Since machine learning already predicted that there's a mistake in this problem, in this product, they will check it physically and they will find out that, oh, there's no mistake, everything is fine. So then they will repackage and say, okay, it can go to the customer. So they are double checking to be on the safer side. So this is a mistake that is a little bit acceptable, but this is no-go area when it comes to production processes. But for medical, you can see it's opposite. So that's why it's good to have a deep analysis of your result. It's not just enough to just tell us, I got 97% accuracy and that's all. No, you need to go more deeper into it and let us know the implication of what you have actually gotten. Especially if you are comparing your work with people who work in the area before. The same data set have been used before. It becomes even more, it becomes very compulsory for you to try to come up with the analysis. However, if you are working, this is an example of classification problem. Let's say you are working with what we call you are working with regression problem. You are predicting the strength of a material, which is going to be in number. See, in addition to telling us the accuracy, see what is the correlation coefficient you have achieved, what is the root mean square error. These are all in number. We also encourage you to make plots. You make plots. Plot for us what we call the scatter plot of the predicted versus, this is predicted value, this is the original value. These are the original value. You plot them, and then you plot the predicted value on top of them. Let's see how the prediction is passing through the original. See, you plot something like this, you can see that the prediction passes through some of them while missing some of them. So this is going to show us in kind of pictorial form how far your prediction is actually closer to the actual value that you have been given. So this is for regression problem. When you are solving regression problem, you might need to support your result. It's not just enough to have the table. So you have to have pictorial representation that will also try to match the, using scatter plot or thereabout, that will be able to match the predicted and the actual value side by side, so that you can be able, people can be able to appreciate how accurate the predictions are coming. So, and other ways that we can also represent our output also here in the classification, we talk of the ROC, the PR, ROC, and so many other curves that you might need to use to support your work. So we're going to discuss all those other things later on as we go into the practical demonstration of how to document the outcome of our research. So this is to tell us that discussion of results is not just for you to lift what is in the table and reproduce it under the discussion. No, you go higher by telling us, try to interpret the result. What does it mean? Tell us more implication of what has been done. And of course, finally, you're going to conclude what you have done, the conclusion of your work. So what you have done, what you want to actually achieve. So continue, like I was saying, so this is Friday, we move to conclusion. So we started from the introduction, literature survey, we call the formulation of your problem. This is where majority of us are now in the research groupings that we are. So let us move on that. So I have clarified the fact that you have a very nice topic and you have seen someone who published a paper in that area. It doesn't mean you can still not contribute in that area. So try to dig in, check what has been published, try to identify the gaps. If we run into any trouble identifying the gaps, we can please refer it to me for more guidance on how to do that, because it takes time. There will always be a way that you can contribute. So seeing something that's been published in your intended area, it's not something to push you off. Rather, you move further and get more detail about what has been published, and then you can establish the gaps that are still available. And also, we talk about the methodology, we've talked about the data analysis, discussion, and then the conclusion, got the references and whatever penalty we had. So this is as regard the general framework of doing research with machine learning. So next level, we're going to be talking about, Shalaba, next week, hopefully, we'll be starting to describe practically how do we document or how do we write research paper from machine learning point of view. When you use machine learning to solve problem, how do we write the research paper? We're going to take it from the beginning, abstract writing, introductory writing, and especially describing the methodology. I mean, from the point of view, the algorithm that we are going to use, and then going down to the actual empirical study. So how you're going to describe your data, what information you need to provide in your data, about your data, and what kind of processing you need to do on your data, and the different kind of experiment, and how you can report their result and outcomes. So inshallah, we'll be looking into this one in our next gathering. Before we finish this section and go to question time, use this opportunity to just remind us that especially under the methodology, or when you are going to document your work, it's very important that we're going to describe the algorithms. Description of algorithm is very important, and it's good you describe the algorithm from mathematically, not just providing a kind of tutorial-like presentation of the algorithm, but rather a kind of mathematical representation of the algorithms. Since if you are adding new things to the algorithm, that's excellent. But if you are using already existing algorithm, that is also fine. It is allowed. But then you need to present it in mathematical way. So, and that is why we have mathematicians in our midst, and I will encourage the mathematician in our midst to kindly feel free to join most of the teams because they are going to be in need of such mathematicians during the description of the algorithms. Because the mathematician will have to study the algorithm and write it out in a mathematical form, sometimes different from what is existing in literature. I mean, write it from another angle, especially to avoid plagiarism. Yeah, you can take an algorithm from earlier published work, which is okay, of course, with citation, but then we all know about the plagiarism issue that you have to maintain ethical writing, which means the level of matching that is allowed is limited. So in this case, a professional mathematician will look into it critically. The same thing will be written in another form using different, they know this is their own work actually. So they know the same idea will be presented in a totally different way while still achieving the same results. So prevent the problem of non-ethical writing. So this is a kind of a call to some of our mathematicians in the midst of us that kindly please join some of our teams. So they are definitely going to be in need of our service as they move on to the next stage in the development of machine learning, experiment, and research writing. So once again, thank you. I think that's what we're going to have here for the day. So we're going to move to question time. If you have any questions from the audience, so we're going to take some questions before we call it a day, while we look forward to, inshallah, next week. So we're going to go into practical documentation training on how can we write the outcome of what we have done. So presenting it hopefully in a manner that will be acceptable to the topmost journal in our various field of endeavor. Thank you very much, and you are welcome. Alhamdulillah.